Okay, so I left off on recording 3 on this table, the statistical decision process table, where we had 4 possibilities. I had to stop early because my next slide had to be fixed. So anyway, this is recording 4 for topic 9. Okay. And we are going to start off with talking about type 1 error in a little bit more detail. This is when we reject a null hypothesis is true. So look back on this screen right here. Okay, it's a false positive when in reality null is true, but we reject it. Okay, it's a false positive. We conclude the predicted relationship exists when it really does not. Okay, the probability of making a type 1 error is always alpha, usually 0.05. And this can happen for a sampling error, right? So this is why it's so important to replicate. Remember the sampling distribution of means? The mean of the sampling distribution of means is going to be equal to the population mean, but sometimes it takes more than one sample, right? And when we have set the alpha at 0.05, this means we're willing to accept the fact that 5% of the time we could be wrong, right? In a simplistic way to put it, right? Okay, so we also have type 2 error, which is called beta error. This is when you fail to reject a null hypothesis that is actually false. This often results from too small a sample, false negative. We conclude that our predicted relationship does not exist when it really does. The probability of a type 1 error is equal to beta, right, which is 1 minus power. Now, what's power? Statistical power refers to the probability of rejecting a false null hypothesis, right? It's influenced by beta, which is the type 2 error rate, right? Power equal 1 minus beta. The effect size, how big is the effect? Think back to our calculations for Z. Remember when we have the numerator is always our sample mean minus the null hypothesis mean or the population mean. So the bigger that difference, the larger the numerator. So the more likely we're going to get a Z score that is more extreme than the critical Z value, right? Alpha. So the larger the alpha, the greater your power. But on the other hand, also the greater your chances of making a type 1 error, right? Your sample size, larger sample size, the better your power, the greater your power. And then the standard deviation of the population. So the smaller the standard deviation, the greater your power. Because remember that standard deviation is in the denominator, right? So the smaller it is, that means the higher the value of your obtained Z or T or whatever. So the biggest thing that we can manipulate here is the sample size. We can't change the effect size. It is what it is, right? We can measure it better. That increases it, but we can't really change it. Okay. Sample size we can change. It's really important to calculate how many people we need before we start collecting the data so we know when to stop. And we do that by using a power analysis, right? Power analyses are beyond the scope of this course, but they're really important if you ever get to the point where you're conducting research yourself, all right? So that power analysis goes on and happens during the designing of the study, right? Before you start collecting data, right? We are focusing here on the testing predictions, on the using statistical analyses and our scientific method and thinking and all the hypothesis testing steps, right? So back to our hypothesis testing step, we have to set a decision rule, right? What goes into stating this decision rule? And we want to do it before we test our hypotheses. We'll ideally do it before we collect the data and so forth, right? But you guys are using data that already exists. So first, we need to decide if we want a one-tailed directional test or a non-directional or two-tailed test. Okay, do we care if the results occur in one direction or is either direction interesting? Now, the best study designs are those in which either result is interesting, right? The truly best are the ones that even if you don't get a result, it's interesting, right? So this is usually the case, right? You find our Z criteria corresponding to our decision, okay, or we set the alpha value. So 1.96, more Z of more extreme than 1.96 is our critical Z value for a two-tailed test at alpha level of 0.05, right? You have to do this before you look at your results, before you even run the analyses, right? You establish them, you set them first, okay? So for example, I hypothesize that people with stronger religious faith will be more self-forgiving. This is a positive correlation being predicted here, right? So it's a one-tailed test with our alternative hypothesis, which corresponds to our research hypothesis, rho greater than 0, a positive correlation. Our null hypothesis, rho less than or equal to 0. Null is always equal to 0. Our criterion, alpha equals 0.05, and our decision rule is reject the null if p less than 0.05. We collect the data and look what we get. We get a Pearson's R of negative 0.04, p-value of 0.438. All right, so remember, reject if p less than 0.05. Well, 0.438 is clearly greater than 0.05, so we fail to reject the null, right? Fail to reject the null. So I'm going to write that out because I know people often get confused here, right? So remember, our decision rule was reject. It's messy and it's cursive. Null if p less than 0.05. We compare 0.05 to 0.438. We see that p is greater than 0.05, so we fail to reject the null. All right, make sure you have that clear. Plain English, people's religious faith was not related to their self-forgiveness in this sample. All right. And that's it for here. Don't forget to do the correlation review quiz on Canvas and email me if you have any questions.